Tonight, we'll drift gently through our cosmic neighborhood, exploring the remarkable truths about our solar system. From the glowing surface of the Sun to the frozen reaches beyond Neptune, from volcanic moons to diamond rain falling through distant atmospheres, we'll discover the gentle wonders that surround our small blue world. Welcome to Get Sleepy Science. I'm so glad you found your way here tonight. Wherever you are right now, perhaps with the windows closed against the night, or with the gentle hum of quiet around you, allow yourself to settle into this shared moment of stillness. We'll explore the remarkable truths about our solar system, from the Sun's glowing corona where spacecraft now fly, to Jupiter's volcanic moons erupting with more power than all of Earth's power plants combined, to Neptune, where diamonds rain through hydrogen clouds. Let these cosmic facts become your pathway to rest. A gentle like and subscribe helps other stargazers find their way here too. It only takes a moment, but it means the universe to us, one sleepy soul at a time. There's no pressure at all, just a soft tap if these cosmic stories bring you peace. For now, just let your shoulders soften. Let your breathing fall into its own rhythm. Imagine yourself drifting in a space of gentle curiosity, where facts become stories and stories become dreams. The universe is vast, but tonight, this moment is small and safe. Close your eyes and take a deep breath. You're lying in a small spacecraft, drifting gently through the endless night sky, moving without boundaries, without destination, only the light of distant stars and absolute silence. Let go of all limits. Let your mind drift through the solar system. Our sun is not burning the way a fire burns on Earth. Instead, it generates light and heat through nuclear fusion, where hydrogen atoms combine to form helium deep in its core. The temperature at the sun's center reaches about 27 million degrees Fahrenheit. At that temperature and pressure, hydrogen nuclei overcome their natural repulsion and fuse together, releasing tremendous energy. This process has been happening for 4.5 billion years, and it will continue for another 5 billion years or so. Every second, the sun converts about 600 million tons of hydrogen into helium. The light that reaches your eyes right now began its journey in the sun's core, 30,000 to 170,000 years ago, slowly working its way outward before finally streaming across space to Earth. The sun is our neighborhood star, ordinary in cosmic terms, yet extraordinary in how it sustains life on our small planet. In December 2024, NASA's Parker Solar Probe made history by flying closer to the sun than any human-made object has ever traveled. The spacecraft came within just 3.8 million miles of the solar surface, traveling at 430,000 miles per hour. That's fast enough to fly from New York to Tokyo in less than 1 minute. Protected by a carbon foam heat shield, the probe survived temperatures reaching about 3,300 degrees Fahrenheit, while the instruments behind the shield stayed at comfortable room temperature. The mission has revealed that the sun's outer atmosphere is more complex than scientists expected, with magnetic field structures that zigzag in unexpected ways. These discoveries help us understand not only our sun but also how other stars work throughout the galaxy. And the spacecraft continues its mission, gathering data from a place we've only dreamed of reaching until now. Mercury, the closest planet to the sun, experiences the most extreme temperature swings in the solar system. During its day, which lasts about 59 Earth days, the sunny side can reach temperatures of 800 degrees Fahrenheit. But Mercury has almost no atmosphere to trap and distribute heat, so when night falls, temperatures plummet to minus 280 degrees Fahrenheit. That's a difference of over 1,000 degrees between day and night. Despite being so close to the sun, Mercury actually has water ice hiding in permanently shadowed craters near its poles, where sunlight never reaches. The planet's surface is covered in ancient impact craters, looking much like Earth's moon. Mercury also has a large iron core that makes up about 70% of the planet's radius, which scientists think may have formed when a massive impact early in the planet's history, stripped away much of its outer layers. It's a world of extremes, silently orbiting our star every 88 Earth days. Venus, Earth's closest planetary neighbor, rotates backward compared to most planets in the solar system, while Earth and most other planets spin counterclockwise when viewed from above the North Pole. Venus spins clockwise. Scientists call this retrograde rotation, and they're not entirely sure what caused it. One theory suggests a massive collision long ago knocked Venus into this unusual spin. What makes this even stranger is that Venus rotates incredibly slowly. One day on Venus lasts 243 Earth days, which means a Venusian day is actually longer than a Venusian year. The planet completes one orbit around the Sun in just 225 Earth days. So on Venus, the Sun rises in the west and sets in the east, and it does so incredibly slowly, taking months to cross the sky. These peculiar rotational characteristics make Venus one of the most unusual planets in our solar neighborhood. Our Earth sits at just the right distance from the Sun to support liquid water on its surface. Scientists call this the habitable zone, though sometimes it's known as the Goldilocks zone, because conditions are not too hot and not too cold, but just right. If Earth were just 5% closer to the Sun, all the water would evaporate. If it were 20% farther away, the oceans would freeze solid. But Earth's position is only part of the story. Our atmosphere, with its blanket of gases including carbon dioxide and water vapor, helps trap enough heat to keep temperatures moderate. Earth's magnetic field shields us from harmful solar radiation. The Moon stabilizes Earth's tilt, preventing wild swings in climate. All these factors together create conditions where liquid water remains stable and where life as we know it can flourish. We orbit in what could be called a quiet, protected corner of the galaxy, on a planet perfectly suited to the life that evolved here. The Moon is gradually moving away from Earth at a rate of about 1.5 inches per year. Scientists discovered this by bouncing laser beams off reflectors that astronauts placed on the Moon's surface during the Apollo missions. By measuring how long it takes for the laser light to return, they can calculate the Moon's distance with incredible precision. This slow recession happens because of tidal forces between Earth and the Moon. As Earth's oceans rise and fall with the tides, they create friction that gradually slows Earth's rotation. To conserve angular momentum in the Earth-Moon system, the Moon drifts farther away. Billions of years ago, the Moon was much closer, and Earth's day was much shorter, perhaps only 5 or 6 hours long. In the distant future, Earth's rotation will slow enough that one side will always face the Moon, just as the Moon already shows us only one face. But this will take billions of years to occur, and by then, the Sun will have changed in ways that affect both worlds far more dramatically. Mars, the fourth planet from the Sun, appears red because its surface is rich in iron oxide, which we commonly call rust. But this rust didn't form the way rust forms on Earth, through interaction with liquid water and oxygen in an atmosphere. Instead, Mars's iron-rich rocks have been weathered over billions of years by ultraviolet radiation from the Sun and by chemical reactions with the planet's thin atmosphere. The fine dust created by this process covers much of the planet's surface and gets blown into the atmosphere by winds, sometimes creating dust storms that can envelop the entire planet. These global dust storms can last for months. From Earth, Mars has appeared red in the night sky for as long as humans have looked up, which is why ancient cultures often associated it with war and bloodshed. But up close, Mars reveals a more subtle palette. The dust is rust-colored, yes, but the rocks show grays, browns, and golds, and the polar ice caps gleam white with frozen water and carbon dioxide. In July 2024, NASA's Perseverance rover discovered a rock on Mars nicknamed Chayava Falls that contains potential signs of ancient microbial life. The rock, found in an ancient riverbed called Neretva Vallis, shows a pattern of dark and light spots that scientists call leopard spots. On Earth, similar patterns often form through biological processes or through chemical reactions that could provide energy for life. The rock contains organic molecules, minerals including vivianite and greigite, and shows evidence that water once flowed through it. After a year of careful study, scientists published their findings in September 2025 in the journal Nature. They found no strong evidence for non-biological explanations of these patterns. However, scientists emphasize that this is a potential biosignature, not definitive proof of life. To know for certain, the rock sample would need to be brought back to Earth for more detailed analysis. It represents the closest we've come so far to finding evidence that Mars once hosted microbial life billions of years ago. The largest volcano in the solar system is Olympus Mons on Mars, which rises about 13.5 miles above the surrounding plains. That's nearly 2.5 times the height of Mount Everest. But what makes Olympus Mons truly extraordinary is its size in all dimensions. Its base is roughly 370 miles across, about the size of the state of Arizona. If you stood at the edge of Olympus Mons, the summit would be beyond your horizon. The volcano's slopes are so gentle that if you walked up its side, you might not even realize you were climbing a mountain until you were quite high up. Olympus Mons formed over billions of years through countless eruptions, with each flow adding another layer of solidified lava. Mars lacks plate tectonics, so volcanic hotspots stay in one place for eons, allowing volcanoes to grow to enormous sizes. Olympus Mons is probably no longer active, but it stands as a testament to Mars's volcanic past. A mountain so large it seems impossible even as we look at images of it from spacecraft orbiting the red planet. Jupiter, the largest planet in our solar system, is so big that more than 1,300 Earths could fit inside it. Yet, despite its enormous size, Jupiter is made almost entirely of hydrogen and helium, the lightest elements in the universe. If you could somehow place Jupiter on a scale, you'd find it weighs about 318 times as much as Earth. But if you calculated its average density, you'd discover it's less dense than water. Jupiter is essentially a giant ball of gas, though at great depths, the pressure becomes so intense that hydrogen exists in a strange metallic liquid form. The planet rotates faster than any other world in the solar system, completing one rotation in just under 10 hours. This rapid spin causes Jupiter to bulge at its equator. Powerful winds, organized into bands of clouds that circle the planet, can reach speeds of 400 miles per hour. Jupiter's Great Red Spot, a storm that has raged for at least 300 years, is large enough to swallow multiple Earths. It's a world of extremes, a gas giant that dominates its region of the solar system. Jupiter's moon Europa has captured scientists' imaginations for decades, because beneath its icy shell lies what may be the largest ocean in the solar system. While Europa is only about the size of Earth's moon, scientists think its ocean could contain twice as much water as all of Earth's oceans combined. The ice shell covering this ocean is estimated to be 9 to 15 miles thick, though in some places it might be much thinner. Europa's ocean remains liquid because tidal heating from Jupiter keeps the interior warm. As Europa orbits Jupiter in an elliptical path, the giant planet's gravity stretches and squeezes the moon, generating heat through friction. In October 2024, NASA launched the Europa Clipper mission, the largest spacecraft NASA has ever built for a planetary mission. After using gravity assists from Mars and Earth, the spacecraft will arrive at Jupiter in April 2030 to conduct 49 close flybys of Europa, searching for signs that this hidden ocean might harbor the ingredients necessary for life. Io, another of Jupiter's moons, is the most volcanically active body in the solar system. More than 400 active volcanoes dot its surface, and eruptions are happening constantly. In December 2024, NASA's Juno spacecraft detected the most powerful volcanic eruption ever observed on Io. The hotspot was larger than Lake Superior and released energy 6 times greater than all of Earth's power plants combined. Scientists think this enormous eruption came from multiple connected volcanic vents erupting simultaneously, suggesting a vast, underground magma system. Io's volcanic activity is powered by the same tidal heating that warms Europa's ocean. But because Io is closer to Jupiter and doesn't have a thick ice shell to absorb the flexing, the heat manifests as volcanism instead. The eruptions shoot material hundreds of miles into space, and sulfur compounds from the volcanoes give Io its distinctive yellow, orange, and red colors. New volcanoes continue to form, and the surface is so geologically active that there are no impact craters visible anywhere. The entire surface is constantly being renewed by volcanic activity. Ganymede, the largest moon in the solar system, is even bigger than the planet Mercury. Measuring about 3,270 miles across, Ganymede is the only moon known to have its own magnetic field. This magnetic field creates a miniature magnetosphere around Ganymede, nested within Jupiter's much larger magnetosphere. Scientists think Ganymede's magnetic field is generated by convection of liquid iron deep within a metallic core, similar to how Earth's magnetic field forms. Beneath Ganymede's icy surface, there likely exists a liquid water ocean, making it yet another moon in the Jupiter system that might harbor conditions suitable for life. The surface shows a mix of 2 types of terrain: dark, heavily cratered regions that are billions of years old, and brighter regions with grooves and ridges that appear to be younger. These brighter areas may have formed when liquid water erupted from below and froze, resurfacing portions of the moon in a process called cryovolcanism. Ganymede orbits Jupiter once every 7 days and is always locked with the same face toward the planet. Callisto, the outermost of Jupiter's 4 large Galilean moons, has the most heavily cratered surface of any object in the solar system. Every inch of its surface is covered with impact craters, suggesting that Callisto's surface is ancient and has remained largely unchanged for billions of years. Unlike Europa, Ganymede, and Io, Callisto doesn't experience much tidal heating because its orbit is more circular and it's farther from Jupiter. This means its interior hasn't been warm enough to drive geological activity that would erase craters. Yet despite its ancient, quiet surface, scientists believe Callisto may also hide a subsurface ocean beneath its ice and rock layers. If this ocean exists, it would be very deep, perhaps 60 to 120 miles below the surface. Callisto's lack of geological activity makes it an ideal place to study the solar system's early history, as its surface preserves a record of impacts from the solar system's violent youth. Some scientists have even suggested that Callisto would be a good place for a future human base, because its distance from Jupiter means less radiation exposure compared to the inner moons. Saturn, the second largest planet in our solar system, is famous for its magnificent ring system. But what many people don't realize is just how extensive those rings are. If you could look at Saturn from above, the rings would span more than 175,000 miles from edge to edge. That's nearly 3/4 of the distance between Earth and the Moon. Yet, despite their enormous width, the rings are incredibly thin. The main rings are typically only 30 to 100 feet thick. If you made a scale model where the rings were as thin as paper, they would be about half a mile in diameter. The rings are made of billions of chunks of ice and rock, ranging in size from tiny grains to pieces as large as houses. They orbit Saturn at different speeds depending on their distance from the planet, creating intricate patterns and gaps. Scientists are still not entirely certain how the rings formed, but one theory suggests they may be the remains of a moon that was destroyed by an impact or tidal forces, or they might be leftover material from Saturn's formation that never coalesced into a moon. Titan, Saturn's largest moon, is the only moon in the solar system with a thick atmosphere. In fact, Titan's atmosphere is denser than Earth's. If you stood on Titan's surface wearing a spacesuit, you'd feel a pressure about 50% greater than what you feel at sea level on Earth. The atmosphere is mostly nitrogen, just like Earth's, but with significant amounts of methane and other organic molecules. What makes Titan truly remarkable is that it has a complete methane cycle, similar to Earth's water cycle. Liquid methane evaporates from lakes and seas, forms clouds, and falls as rain. Rivers of liquid methane carve channels in Titan's surface. There are lakes and seas of liquid methane and ethane at the poles. Seasonal weather patterns move across the moon. The Cassini mission, which studied Saturn and its moons from 2004 to 2017, revealed Titan to be one of the most Earth-like bodies in the solar system, despite being so cold that water ice is as hard as rock and methane exists as a liquid. Enceladus, a small moon of Saturn, only about 300 miles in diameter, has proven to be one of the most exciting discoveries in planetary science. In 2005, the Cassini spacecraft detected plumes of water vapor and ice particles erupting from cracks near Enceladus's south pole. These plumes shoot hundreds of miles into space, and analysis revealed they contain not just water, but also organic molecules, salts, and silica particles. The presence of these materials strongly suggests that Enceladus has a liquid water ocean beneath its icy shell, and that this ocean is in contact with a rocky seafloor where interesting chemistry could be happening. The geysers are thought to erupt because tidal heating from Saturn warms the interior, keeping water liquid despite the moon's great distance from the sunday. Some of the material from these plumes escapes Enceladus entirely and becomes part of Saturn's E-ring. Scientists consider Enceladus one of the best places in the solar system to search for life, because it combines liquid water, organic molecules, and an energy source in an environment that might be habitable. Uranus is tilted on its side in a way that no other planet is. While most planets spin roughly upright as they orbit the Sun, Uranus spins on its side, with its axis of rotation tilted 98 degrees from vertical. This means that Uranus essentially rolls around the Sun like a ball rolling on a floor. During parts of its orbit, one pole points almost directly at the Sun and experiences continuous daylight for decades, while the other pole experiences continuous night. Then, as Uranus continues its 84-year journey around the Sun, the seasons reverse. Scientists think a massive collision with an Earth-sized object early in the solar system's history knocked Uranus onto its side. This collision may have also affected the planet's interior structure and heat distribution. Uranus emits less heat from its interior than the other giant planets, possibly because the collision disrupted how heat flows through the planet's layers. With its pale blue-green color from methane in its atmosphere and its unique rotational tilt, Uranus remains one of the most unusual worlds in our solar system. Deep inside Uranus and Neptune, diamonds may be raining through the interior layers of the planets. Scientists have long hypothesized this possibility, and recent experiments in 2024 have provided the strongest evidence yet. Using powerful lasers to recreate the extreme pressures and temperatures found thousands of miles below these planets' surfaces, researchers compressed plastic materials rich in carbon and hydrogen. At these conditions, the carbon separated from hydrogen and crystallized into diamonds, which then sank through the surrounding material like rain falling through air. The new experiment showed that diamond formation can happen at lower pressures and temperatures than previously thought, meaning diamonds could form at shallower depths within Uranus and Neptune. These sinking diamonds could help explain why these planets have unusual, lopsided magnetic fields that don't align with the planet's rotation axis. As the diamonds fall, they could stir conducting fluids in the planet's interiors, generating the odd magnetic fields we observe. Billions of diamonds, some possibly growing to enormous sizes over millions of years, may be slowly drifting toward the cores of these distant ice giants. Neptune, the most distant of the 8 planets, experiences the fastest winds in the solar system. Measurements from the Voyager 2 spacecraft and later observations from the Hubble Space Telescope have recorded wind speeds reaching 1,200 miles per hour. That's about 5 times faster than the strongest hurricanes on Earth. What makes this even more puzzling is that Neptune receives very little energy from the Sun, being 30 times farther from the Sun than Earth is. The sunlight reaching Neptune is about 900 times weaker than what we receive on Earth. Yet, Neptune somehow generates enough internal heat to drive these incredibly powerful winds. Scientists think Neptune must be releasing heat left over from its formation, or perhaps heat generated by gravitational compression in its interior. The atmosphere shows bands of clouds and storms, including a great dark spot similar to Jupiter's Great Red Spot, though Neptune's spots appear and disappear over periods of a few years. Neptune's deep blue color comes from methane in its atmosphere, which absorbs red light and reflects blue light back into space. Pluto, reclassified as a dwarf planet in 2006, surprised scientists in many ways when NASA's New Horizons spacecraft flew past it in 2015. Instead of finding a dead, inactive world, New Horizons revealed that Pluto is geologically active. The spacecraft discovered ice mountains as high as the Rocky Mountains on Earth, made of frozen water, ice as strong as rock at those temperatures. It found vast plains of frozen nitrogen ice that appeared to be flowing in patterns similar to glaciers. Some regions looked less than 10 million years old, incredibly young in geological terms. Scientists spotted what might be ice volcanoes that erupt mixtures of water, nitrogen, ammonia, and methane instead of molten rock. Pluto has a thin atmosphere that freezes and falls as snow when the dwarf planet is farther from the Sun in its highly elliptical orbit, then sublimes back into gas when Pluto moves closer to the Sunday. A large heart-shaped region called Tombaugh Regio dominates one hemisphere. All this activity on a world so small and so far from the Sun suggests that planetary geology can be active in ways scientists hadn't imagined. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, but it's not the crowded, dangerous place that movies often portray. If you were traveling through the asteroid belt in a spacecraft, you'd likely see nothing but empty space. The asteroids are spread so far apart that the average distance between them is hundreds of thousands of miles. All the asteroids combined have only about 4% of the Moon's mass. Most of that mass is concentrated in the 4 largest objects: Ceres, Vesta, Pallas, and Hygiea. Ceres alone contains about 1/3 of the total mass of the asteroid belt. These objects are remnants from the solar system's formation, rocky and metallic material that never coalesced into a planet, possibly because Jupiter's gravity stirred them up too much. The asteroid belt preserves a record of the solar system's early chemistry. By studying asteroids, scientists can learn about the building blocks that formed the planets. Some asteroids even contain water-rich minerals and organic molecules, suggesting they may have delivered these important ingredients to Earth billions of years ago. Ceres, the largest object in the asteroid belt, was upgraded to dwarf planet status at the same time Pluto was downgraded. Dawn spacecraft observations from 2015 to 2018 revealed that Ceres is much more interesting than anyone expected. The dwarf planet has a large amount of water ice mixed with rock. Some estimates suggest Ceres could have as much fresh water as Earth does, though it's mixed throughout the interior rather than forming a liquid ocean. The surface shows over 100 bright spots, which turned out to be deposits of salt minerals left behind when briny water reached the surface and evaporated. One of these bright spots, located in a crater called Ocata, has been actively depositing new salt within the past 2 million years, suggesting that briny liquid may still exist below Ceres's surface. Scientists found evidence for a past subsurface ocean and possibly pockets of brine that persist today. Ceres also has at least one mountain, Ahuna Mons, that appears to be a cryovolcano, a volcano that erupted icy material instead of lava. For such a small world, Ceres shows surprising complexity. Beyond Neptune, lies the Kuiper belt, a vast region of icy bodies left over from the solar system's formation. This belt extends from about 2.8 billion miles from the Sun to around 4.6 billion miles. One astronomical unit is the distance from the Earth to the Sun, so the Kuiper belt begins where Neptune orbits and extends outward for billions more miles. The Kuiper belt contains hundreds of thousands of objects larger than 60 miles across, and probably billions of smaller ones. Pluto is one of the largest known Kuiper belt objects. These bodies are mostly made of frozen volatiles, like water, methane, and ammonia. Some scientists think that in October 2025, evidence emerged suggesting there might be another planet, temporarily called Planet Y, in the outer solar system beyond the Kuiper belt. This hypothetical planet would be smaller than Earth, but larger than Mercury, and it could influence the orbits of distant Kuiper belt objects. Whether or not this planet exists, the outer solar system clearly holds secrets we're still uncovering. Comets are sometimes called dirty snowballs or icy dirt balls, and both descriptions fit. These objects are mixtures of frozen water, frozen gases like carbon monoxide and methane, rocky dust, and organic compounds. Most comets come from two regions, the Kuiper belt and the much more distant Oort cloud, which surrounds the solar system in a vast spherical shell beginning at thousands of astronomical units from the Sunday. When a comet's orbit brings it close to the Sun, solar heating causes the ice to sublimate, turning directly from solid to gas without becoming liquid. This gas, along with dust particles, streams away from the comet's nucleus, forming the characteristic tail that can stretch for millions of miles. Comets always point their tails away from the Sun, pushed by solar radiation and the solar wind. Some comets visit the inner solar system frequently, while others take thousands or millions of years to complete one orbit. When comets pass through the inner solar system repeatedly, they gradually lose their volatile ices and eventually become inactive, looking much like asteroids. Scientists study comets because they contain pristine material from the solar system's formation, essentially time capsules from 4.5 billion years ago. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the astronauts we send to the heavens, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronauts breathed while looking down at Earth from above. We are all space travelers, flying on a small planet through the galaxy. Now we continue. The Sun loses about 4 million tons of mass every second through nuclear fusion. This might sound alarming, but considering the Sun's total mass of about 2 times 10 to the 30th power kilograms, it's barely noticeable. The Sun has been shining for 4.5 billion years and will continue for another 5 billion. Over its entire life, it will convert only about 7% of its hydrogen into helium. Eventually, when the hydrogen fuel in the core runs low, the Sun will expand into a red giant, large enough to possibly engulf Earth's orbit. After that phase, it will shed its outer layers and settle down as a white dwarf, a hot but dim remnant about the size of Earth. This is the fate awaiting most stars of the Sun's size. The light we depend on, the energy that powers all life on Earth, comes from a process that's slowly consuming the Sun's mass, so slowly that countless generations will live and pass beneath its steady warmth. When NASA's Parker Solar Probe flies through the Sun's corona, it's traveling through temperatures exceeding 1 million degrees Fahrenheit. Yet, its heat shield only reaches about 1,800 degrees. This seems impossible until you understand the difference between temperature and heat. Temperature measures how fast particles are moving. In the corona, particles move incredibly fast, giving it a very high temperature. But the corona is extremely thin, with very few particles in any given volume. Heat transfer depends on particles colliding with an object. With so few particles present, even though they're moving rapidly, they don't transfer much heat to the spacecraft. It's similar to how your hand can survive briefly in a hot oven where air temperature is 400 degrees, but touching a metal tray at the same temperature would immediately burn you. The Parker Solar Probe's innovation was recognizing this principle and designing a heat shield that could reflect and radiate away the limited amount of heat it receives. Venus's surface pressure is about 90 times greater than Earth's atmospheric pressure at sea level. That's equivalent to the pressure you'd experience if you were half a mile deep in Earth's ocean. This crushing pressure, combined with surface temperatures around 870 degrees Fahrenheit, makes Venus the most inhospitable planet for spacecraft to visit. Thick clouds of sulfuric acid float in the atmosphere. The atmosphere is almost entirely carbon dioxide, creating a runaway greenhouse effect. Scientists think Venus may once have had oceans like Earth, but as the sun gradually brightened over billions of years, Venus's water evaporated. Water vapor strengthened the greenhouse effect, temperatures rose further, and eventually all the water was lost to space. Now, Venus is a cautionary tale about greenhouse warming taken to its ultimate extreme. Soviet spacecraft managed to land on Venus's surface several times, but the longest any spacecraft survived was about 2 hours before succumbing to the heat and pressure. Earth's atmosphere is just thin enough and thick enough. If it were significantly thinner, we'd be exposed to harmful radiation, and temperatures would swing wildly between day and night. If it were thicker, we'd experience crushing pressures and could be cooked by greenhouse warming. Our atmosphere is roughly 60 miles deep before it fades into the near vacuum of space, though 99% of the atmospheric mass lies within 20 miles of the surface. The atmosphere developed over billions of years. Early Earth's atmosphere was very different, probably rich in carbon dioxide and nitrogen, but lacking oxygen. Photosynthetic organisms gradually added oxygen, transforming the atmosphere into one that could support animals. The oxygen we breathe was created by countless tiny organisms over billions of years. Every breath connects us to that ancient history, to the slow work of life changing a planet. Earth's magnetic field extends far into space, forming a protective bubble called the magnetosphere. This field deflects most of the charged particles streaming from the sun in the solar wind. Without this protection, these particles would gradually strip away our atmosphere and bombard the surface with radiation. Mars lost most of its atmosphere billions of years ago, partly because it lost its magnetic field. Earth's magnetic field is generated by convection of molten iron in the outer core. As the liquid metal moves, it generates electric currents, which create magnetic fields. The field's north and south magnetic poles don't align perfectly with the geographic poles, and they slowly wander over time. Every few 100,000 years, the magnetic field reverses, with north and south poles swapping positions. We can see this recorded in rocks that preserve the direction of the magnetic field when they formed. These reversals seem to happen irregularly, and scientists aren't entirely sure what triggers them. The Moon always shows the same face to Earth because its rotation period matches its orbital period, a phenomenon called tidal locking. It takes the Moon about 27 days to spin once on its axis and 27 days to orbit Earth. This synchronization wasn't always the case. Early in its history, the Moon probably rotated faster. Over billions of years, Earth's tidal forces gradually slowed the Moon's rotation until it became locked. The far side of the Moon, often incorrectly called the dark side, receives just as much sunlight as the near side. We simply never see it from Earth. The far side looks quite different from the near side. It has far more craters and fewer dark plains of volcanic rock. Scientists think this is because the crust is thicker on the far side, making it harder for volcanic lava to reach the surface. Only spacecraft have seen the far side. First, when the Soviet lunar probe photographed it in 1959. It's a reminder that even our closest neighbor holds landscapes we can only visit through robotic eyes. Mars has the largest canyon system in the solar system. Valles Marineris stretches over 2,500 miles long, 430 miles wide in places, and up to 4 miles deep. If placed on Earth, it would stretch across the entire United States, from coast to coast. Unlike the Grand Canyon on Earth, which was carved by the Colorado River over millions of years, Valles Marineris appears to have formed through a combination of tectonic cracking and erosion. Part of the canyon may have opened when the Tharsis volcanic region bulged upward billions of years ago, pulling the crust apart. Later, liquid water and perhaps ice erosion may have widened and deepened the canyons. Some sections show layered sediments that could have formed in ancient lakes. The canyon system connects to chaotic terrain, where massive floods appear to have burst forth, carving channels that flowed north toward the lowland plains. Valles Marineris preserves evidence of Mars's more geologically active past, when forces beneath the surface, and perhaps running water on the surface, shaped its landscape. Jupiter emits more heat than it receives from the Sunday. The planet radiates about 67% more energy into space than it absorbs from sunlight. This excess heat comes from Jupiter slowly contracting under its own gravity. As the planet shrinks very gradually, gravitational potential energy converts to heat. This process has been happening since Jupiter formed 4.5 billion years ago. The heat drives convection in Jupiter's interior, where warm material rises and cooler material sinks. This convection, combined with Jupiter's rapid rotation, organizes the atmosphere into the distinctive bands of clouds we see. The internal heat also powers Jupiter's dramatic weather, including its long-lasting storms. Despite being 5 times farther from the Sun than Earth is, Jupiter remains warm at depth, warm enough that some scientists speculate liquid water could exist in certain layers of its atmosphere, though not at the surface. Jupiter's internal heat is a reminder that worlds don't need to be close to a star to be active and dynamic. Jupiter's magnetosphere is the largest structure made by a planet in the solar system. If you could see it glowing in the night sky, it would appear several times larger than the full moon, even though Jupiter itself is a tiny point of light. The magnetosphere extends several million miles into space on the sunward side and stretches far beyond Saturn's orbit on the side away from the Sunday. This magnetic bubble is generated by convection of metallic hydrogen in Jupiter's interior. Electric currents flow through this conductive fluid, creating powerful magnetic fields. The magnetosphere traps charged particles from the solar wind and from volcanic gases erupted by Io. These particles spiral along magnetic field lines and create intense radiation belts around Jupiter. The radiation is so strong that any spacecraft passing through this region must be specially hardened to survive. Aurorae shimmer around Jupiter's poles, where particles crash into the upper atmosphere. Jupiter's magnetosphere is a complex, dynamic environment, constantly buffeted by the solar wind and fed by material from its moons. Europa's ice shell shows strange features called chaos terrain, areas where the ice appears to have broken apart, shifted, and refrozen. Some chaos terrain regions show blocks of ice that look like they floated before freezing in place, much like icebergs in a slushy Arctic sea. Scientists think these features form when warm ice, or even liquid water from below, softens or breaks through the ice shell, allowing blocks to shift. The chaos terrain is relatively young, perhaps only a few tens of millions of years old. This suggests Europa's ice shell remains active, with material from the subsurface ocean occasionally reaching the surface. If this is happening, it's extraordinarily exciting for the search for life, because it means we might be able to study ocean material without having to drill through many miles of ice. The Europa Clipper mission, launching in 2024, will study these regions in detail, searching for plumes of water vapor that might be erupting from the surface, carrying samples of the ocean into space, where instruments can analyze them. Ganymede's magnetic field creates a miniature magnetosphere, but this magnetosphere sits inside Jupiter's much larger one. The interaction between these two magnetic fields creates fascinating effects. Aurorae flicker at Ganymede's poles, powered by charged particles from Jupiter's magnetosphere. The magnetic field probably shields parts of Ganymede's surface from Jupiter's intense radiation, creating pockets where radiation levels are lower. This could be important if humans ever visit Ganymede, as these magnetically shielded regions would be safer for exploration. The magnetic field also tells us about Ganymede's interior. For a moon to generate its own magnetic field, it needs a liquid, electrically conductive layer deep inside, probably an iron-rich core. This core must be convecting, with hotter material rising and cooler material sinking. The persistence of this core convection 4.5 billion years after Ganymede formed suggests the moon still retains significant internal heat. Ganymede is geologically dead on the surface, but retains a warm, dynamic interior. Saturn's rings are gradually falling toward the planet in a process called ring rain. Charged particles from the rings interact with Saturn's magnetic field, causing some ring material to spiral inward and fall into Saturn's atmosphere. Scientists estimate that the rings are losing between 100 to 300 tons of material every second. At this rate, the rings might disappear within 100 million years, a blink of an eye, in cosmic terms. This discovery came from the Cassini spacecraft's final orbits when it dove between Saturn and its rings. The spacecraft detected streams of organic compounds and water flowing from the rings into the planet's upper atmosphere. If Saturn's rings are young and temporary, it means we're lucky to be living at a time when they exist. 10 million years ago, or 100 million years from now, Saturn might have been, or will be, a ringless planet. The rings we see today might be the remnants of a moon that broke apart relatively recently, or perhaps material captured from a comet or asteroid. Titan's lakes and seas are the only stable bodies of liquid on any world besides Earth. At the surface temperature of -290 degrees Fahrenheit, water is frozen solid, but methane and ethane remain liquid. Titan has hundreds of small lakes and several large seas near its poles. The largest, Kraken Mare, covers about 155,000 square miles, larger than the Caspian Sea on Earth. The depth of these seas is uncertain, but radar measurements suggest some could be hundreds of feet deep. Waves have been detected on the surfaces of some lakes, probably stirred by winds in Titan's thick atmosphere. Some lakes show shoreline features, suggesting their levels change over time, perhaps with seasonal cycles. The liquid in these lakes isn't pure methane, but a mix of methane, ethane, and dissolved nitrogen. If you could visit Titan's surface, you'd see a landscape eerily similar to Earth's, with clouds, rain, rivers, lakes, and seas, all made from substances that on Earth are gases. Uranus and Neptune are sometimes called ice giants rather than gas giants, even though they're still much larger than Earth. This is because, unlike Jupiter and Saturn, which are mostly hydrogen and helium, Uranus and Neptune contain large amounts of water, methane, and ammonia ices in their interiors. These substances exist in strange states under the extreme pressures inside these planets, not as solid ice and not as liquid water, but as superheated, super-pressurized fluids. The term ice refers to the chemical composition rather than temperature. Interior models suggest Uranus and Neptune have a rocky core surrounded by a thick mantle of these ices in their strange fluid state, with a relatively shallow atmosphere of hydrogen, helium, and methane on top. The exact internal structure remains uncertain because we've only had one close spacecraft visit. Voyager 2 flew by Uranus in 1986 and Neptune in 1989. No other spacecraft has visited these distant worlds since. Neptune has the fastest planetary winds, but it also has the slowest moving clouds in the solar system. Some of Neptune's clouds take more than 16 years to move around the planet. These are not clouds floating in high-speed winds, but rather features embedded in deeper layers of the atmosphere, moving with the planet's rotation. Neptune rotates once every 16 hours, and these slow-moving clouds follow that rotation. The atmosphere above them, however, screams past at incredible speeds. Scientists don't fully understand this decoupling between different atmospheric layers. Neptune's atmosphere shows a surprising amount of weather activity for a planet receiving so little solar energy. Large storm systems appear and disappear. The Great Dark Spot, observed by Voyager 2 in 1989, had vanished by the time Hubble looked at Neptune a few years later, but new dark spots have appeared since. Neptune remains mysterious, a world of contrasts, where sluggish deep clouds and record-breaking winds coexist in an atmosphere powered by heat rising from far below. You're still here, still awake, still drifting with us through these cosmic stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I, and everyone listening in the quiet dark, floating through facts like asteroids drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. The Kuiper belt is more than 3 times as wide as the entire region from the Sun to Neptune. While the planets occupy a relatively compact disk extending about 2.8 billion miles from the Sun, the Kuiper belt spreads from 2.8 billion miles to about 4.6 billion miles. This vast ring contains remnants from the solar system's formation, icy bodies that never managed to form into planets. Some Kuiper belt objects are quite large. Eris, discovered in 2005, is slightly smaller than Pluto, but more massive, which prompted the debate that led to Pluto's reclassification as a dwarf planet. Makemake, Haumea, and Gong are other significant Kuiper belt objects. Studying these distant worlds teaches us about conditions in the outer solar system billions of years ago, when the planets were still forming and material was scattered and sorted by gravitational interactions. Comets that visit the inner solar system often develop 2 tails, not just one. The dust tail curves behind the comet's motion, following the orbital path. Sunlight pushes on the tiny dust particles, causing them to lag behind the comet's nucleus. The ion tail, made of gas molecules that have been ionized by solar radiation, always points directly away from the Sun because the solar wind, a stream of charged particles, blows it outward. When a comet is approaching the Sun, the ion tail actually points ahead of the comet. After the comet rounds the Sun and begins moving away, the ion tail switches to point behind. The dust tail, heavier and slower to respond, curves more gradually. Sometimes comets develop a third, faint sodium tail, discovered only in the late 20th century. Under ideal conditions on Earth, you can see these multiple tails with binoculars or a small telescope. They're a visible demonstration of how sunlight and the solar wind interact with matter in space. The asteroid Vesta, one of the largest objects in the asteroid belt, has a mountain near its south pole that's 3 times taller than Mount Everest. The mountain, called Rhea Silvia, rises about 13.5 miles above the surrounding terrain. It formed during a massive impact that created a crater covering most of Vesta's southern hemisphere. The impact was so energetic that it excavated material from deep inside Vesta and launched debris into space. Some of that debris eventually fell to Earth as a specific class of meteorites called HED meteorites, standing for Howardite, Eucrit, and Diogenite. By studying these meteorites, scientists learned about Vesta's composition even before spacecraft visited. The Dawn mission orbited Vesta from 2011 to 2012, revealing a complex, differentiated body with an iron core, a rocky mantle, and a thin crust. Vesta is essentially a small planet that stopped growing billions of years ago, a fossil from the solar system's early days. The Oort cloud, a vast spherical shell of icy bodies surrounding the solar system, begins at about 186 billion miles from the Sun, and might extend as far as 9.3 trillion miles reaching nearly halfway to the nearest star. The Oort cloud is theoretical in the sense that we haven't directly observed it, but its existence is strongly implied by the comets we see. Some comets have orbital periods of millions of years, returning to the inner solar system from great distances. The Oort cloud probably contains trillions of icy bodies, but they're spread across such an enormous volume of space that they're impossibly far apart and faint to see with current telescopes. Occasionally, the gravity of a passing star or the tidal forces of the galaxy nudges an Oort cloud object, sending it falling toward the inner solar system. After spending billions of years in the deep freeze of interstellar space, it warms, develops a tail, and becomes a comet. Saturn's moon Mimas looks like the Death Star from Star Wars because of a huge crater called Herschel that covers about 1/3 of the moon's diameter. The impact that created this crater nearly shattered Mimas. You can see fractures on the opposite side of the moon created by shock waves traveling through Mimas and focusing on the far side. If the impact had been slightly more energetic, Mimas would have broken apart into fragments. The crater's walls rise about 3 miles above the floor, and a central peak rises 4 miles. For such a small moon, only about 250 miles across, these are dramatic features. Mimas, despite its interesting appearance, appears to be geologically dead. Unlike some of Saturn's other moons, it shows no signs of current activity. Its heavily cratered surface suggests it's ancient, preserving a record of impacts from the solar system's early, violent period. Jupiter's moon Ganymede experiences aurorae, just like Earth does, but Ganymede's aurorae are powered by Jupiter. Charged particles from Jupiter's enormous magnetosphere spiral down along Ganymede's magnetic field lines and collide with atoms in the moon's thin atmosphere, causing them to glow. The Hubble Space Telescope detected these aurorae by observing ultraviolet emissions. By studying how the aurorae behave, scientists confirmed that Ganymede has a subsurface ocean. The ocean water affects Ganymede's magnetic field slightly, which in turn affects how the aurorae respond to changes in Jupiter's magnetosphere. This was a clever way to detect an ocean from millions of miles away, using the interaction between Jupiter's magnetic field, Ganymede's magnetic field, and the ocean's effect on that field. Ganymede's aurorae are invisible to human eyes, but tell a story about the moon's hidden depths. Neptune has 14 known moons, and the largest, Triton, is unusual because it orbits backward relative to Neptune's rotation. This retrograde orbit strongly suggests that Triton didn't form alongside Neptune but was captured, probably from the Kuiper belt. Triton is large enough that, if it orbited the Sun instead of Neptune, it would be classified as a dwarf planet, like Pluto. When Voyager 2 flew past Triton in 1989, it discovered a surprising world. Despite surface temperatures of -391 degrees Fahrenheit, making Triton one of the coldest places in the solar system, it's geologically active. Nitrogen geysers erupt from the surface, shooting plumes of gas and dust several miles high. The surface shows cantaloupe terrain, a strange pattern of dimples and ridges unlike anything seen elsewhere. Triton is slowly spiraling toward Neptune because tidal forces are sapping energy from its orbit. In millions of years, it will come close enough to be torn apart by Neptune's gravity, possibly forming a spectacular ring system. Uranus's moon Miranda has one of the strangest landscapes in the solar system. Its surface is a patchwork of different terrains that look as if they were randomly assembled. Smooth plains sit next to regions of parallel ridges and grooves. A feature called Verona Rupes is a cliff that drops about 12 miles, making it the tallest known cliff face in the solar system. Scientists originally thought Miranda might have been shattered by impacts and reassembled, with the different terrains representing pieces that came back together in a jumbled arrangement. A newer theory suggests that tidal heating from Uranus caused ice to melt and resurface parts of Miranda at different times, creating the patchwork appearance. Miranda is so small, only about 290 miles across, that it shouldn't have enough internal heat to drive geological activity. Yet, somehow, it does, or did. Miranda remains a puzzle, a tiny moon with a complex history. The heliosphere is the bubble of space, dominated by the sun's influence. The solar wind flows outward from the sun in all directions until it eventually collides with the interstellar medium, the gas and dust floating between stars. This collision creates a boundary called the heliopause, where the solar wind stops and interstellar space begins. NASA's Voyager 1 spacecraft crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. Both spacecraft are still sending back data, though their power supplies are gradually weakening. The heliosphere protects the inner solar system from some galactic cosmic rays. Outside the heliopause, radiation levels increase. The heliosphere's shape probably isn't perfectly spherical, but is instead somewhat teardrop-shaped, compressed on the side, facing the sun's motion through the galaxy, and stretched out on the opposite side. The sun completes one orbit around the Milky Way galaxy every 225 to 250 million years, a period sometimes called a galactic year. During one galactic year, the entire solar system travels about 5 trillion miles through space. The last time the sun was in its current position in the galaxy, dinosaurs were just beginning to appear on Earth. One galactic year from now, Earth might be unrecognizable, assuming it still exists. The sun moves not just around the galaxy, but also up and down through the galactic plane in a wave-like motion, crossing through the plane every 30 million years or so. This oscillation might correlate with periods of increased comet impacts on Earth, though that hypothesis remains debated. The Sun also has a peculiar motion through space, moving at about 137 miles per second relative to nearby stars. We're cosmic travelers, orbiting the galactic center on a journey that began 4.5 billion years ago and will continue for billions of years to come. Mercury has no moons. In fact, only 2 planets in our solar system lack moons, Mercury and Venus. Scientists think Mercury is too close to the Sun for a moon to maintain a stable orbit. The Sun's gravity would likely pull any moon away from Mercury. Venus might have once had a moon that was destroyed in a collision, or perhaps Venus's slow, backward rotation prevents moons from forming stable orbits. Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all have moons, ranging from Mars's 2 tiny captured asteroids to Jupiter's 79 known moons. Moons form in different ways. Some formed alongside their planet from the same disk of material. Others are captured asteroids or comets. Earth's moon is unusual. It probably formed when a Mars-sized object collided with early Earth, ejecting material that coalesced into the moon. This theory explains why the moon's composition is similar to Earth's mantle and why the moon is so large relative to Earth. The sun's light takes 8 minutes and 20 seconds to reach Earth. Light travels at 186,000 miles per second, and the average distance from Earth to the sun is about 93 million miles. This means when you look at the sun during sunset, you're seeing how it appeared 8 minutes ago. Light from Jupiter takes between 33 and 52 minutes to reach us, depending on where both planets are in their orbits. When Jupiter and Earth are on the same side of the Sun, the light travels faster across the shorter distance. When we're on opposite sides, it takes longer. Light from Neptune takes about 4 hours. Light from the nearest star after the Sun, Proxima Centauri, takes 4.2 years. This growing delay reminds us how vast space is. When we look at distant objects, we're looking back in time. The farther away something is, the older the light we see. Astronomy is the one science where looking outward is also looking backward through time, where studying distance equals studying history. Saturn's moon Enceladus is only about 300 miles in diameter, yet it's one of the brightest objects in the solar system. The surface is covered with fresh, clean ice that reflects almost 100% of the sunlight that hits it. This high reflectivity called albedo, means Enceladus stays very cold. Surface temperatures average around -330 degrees Fahrenheit. Yet, beneath this frozen surface lies a liquid ocean kept warm by tidal heating. The contrast between the frozen surface and warm interior creates the geysers that erupt from cracks near the South Pole. Some of the water from these geysers falls back to the surface as snow, constantly refreshing the surface ice and maintaining its brilliant whiteness. Enceladus is a tiny world with a young surface, an active interior, and quite possibly the ingredients for life. It shines in the darkness of the outer solar system, a beacon of unexpected activity. Jupiter's moon, Io, loses about 1 ton of material every second to volcanic eruptions. Some of this material falls back to the surface, but some escapes into space and forms a vast torus of sulfur and oxygen ions surrounding Jupiter in Io's orbit. This torus is invisible to the human eye, but glows brightly in ultraviolet and radio wavelengths. The ions in the torus interact with Jupiter's magnetic field, creating electrical currents that carry 4 million amperes of electricity between Jupiter and Io. This current generates radio emissions that can sometimes be detected on Earth. Io is essentially connected to Jupiter by an invisible wire of electric current, with Io acting as a generator powered by its volcanic activity. This Io flux tube channels ions from the torus down into Jupiter's atmosphere, creating aurorae at the points where the flux tube connects to the planet. Io's volcanism doesn't just change Io itself, but affects the entire Jovian system. Mars has 2 small moons, Phobos and Deimos, which are probably captured asteroids. Phobos orbits very close to Mars, only about 3,700 miles above the surface, and it's slowly spiraling inward due to tidal forces. In about 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces to form a ring system around the planet. Deimos orbits farther out and is slowly spiraling away from Mars. Both moons are irregularly shaped and heavily cratered. Phobos is the larger of the two, about 17 miles across at its longest. From the surface of Mars, Phobos would appear about 1/3 the size of the Moon as seen from Earth, and it would rise and set twice in one Martian day because its orbital period is so short. Deimos would look more like a bright star than a moon. These tiny moons are interesting remnants of the early solar system, giving us clues about the asteroids that once populated the inner solar system. Saturn's rotation period is uncertain. It sounds strange that we don't know exactly how long a day is on Saturn, but because Saturn is a gas giant with no solid surface, determining its rotation rate is difficult. Different methods give different answers. Watching clouds gives one rate, but clouds move at different speeds, at different latitudes. Measuring radio emissions from Saturn's magnetic field gave another rate during the Voyager missions in the 1980s, but Cassini observations in the 2000s showed a different rate. Scientists now think Saturn's rotation period is about 10 hours and 33 minutes, but this might vary slightly over time. The confusion seems to arise because Saturn's magnetic field is almost perfectly aligned with its rotation axis, and the radio emissions we detect are affected by atmospheric features rather than by the rotation itself. So Saturn keeps one of its most basic properties mysterious. Venus and Uranus are the only planets in our solar system that rotate backward or retrograde. Venus spins very slowly clockwise when viewed from above the North Pole, while most planets spin counterclockwise. Uranus is even stranger because it's tilted so far that it essentially rolls on its side, but its rotation direction is technically retrograde. The cause of these backward rotations probably involves massive collisions early in the solar system's history. A large impact could have delivered enough angular momentum to reverse a planet's spin. In Venus's case, tidal forces from the Sun might have also played a role in slowing and reversing its rotation over billions of years. These unusual rotations remind us that the early solar system was chaotic, with planets forming, migrating, and colliding as they settled into their current orbits. The violence of that time is still visible in the strange spins of these two worlds. Neptune's largest moon, Triton, is gradually approaching Neptune because its retrograde orbit is slowly decaying due to tidal interactions. Eventually, perhaps in 3.5 billion years, Triton will come within Neptune's Roche limit, the distance at which tidal forces become strong enough to overcome a moon's internal gravity. At that point, Triton will be torn apart, and its debris will form rings around Neptune. These rings could rival or even surpass Saturn's rings in splendor, though they would be temporary on cosmic timescales. So future inhabitants of the solar system, assuming any exist, might witness Neptune transforming from a relatively ring-poor planet into a ring-rich one. Triton's destruction is a slow process, invisible within a human lifetime, but inexorable. The moon's fate is sealed by the gravitational embrace of Neptune. Pluto and its largest moon, Charon, are sometimes called a double planet, rather than a planet and moon, because they orbit a common center of mass that lies in space between them, not inside Pluto. When two objects orbit each other in this way, they're technically both orbiting a point in empty space. This configuration is unique among planets and large moons in our solar system. Charon is half the size of Pluto, and they're tidally locked to each other, meaning Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. If you stood on the side of Pluto facing Charon, Charon would hang fixed in the sky, neither rising nor setting. If you stood on the opposite side of Pluto, you would never see Charon at all. The two worlds are locked in an eternal dance, facing each other forever as they orbit the distant Sunday. Asteroid impacts were once much more common in the inner solar system. About 4 billion years ago, during a period called the Late Heavy Bombardment, impacts increased dramatically as leftover debris from planet formation was swept up by gravitational interactions. The Moon preserves a record of this bombardment in its ancient, heavily cratered highlands. Earth was also bombarded, but erosion, plate tectonics, and volcanic activity have erased most evidence. Scientists think this bombardment might have delivered water to Earth, with comets and asteroids carrying ice that melted upon impact. Some impacts were so large they vaporized oceans and sterilized the surface. Yet life arose on Earth despite or perhaps because of this bombardment. Organic molecules might have been delivered along with the water. The violence that shaped the early solar system also may have sown the seeds for life. The solar system's planets orbit roughly in the same plane, called the ecliptic. This plane represents the flattened disk of material from which the planets formed. If you imagine the solar system from the side, all the planets stay within a relatively thin sheet as they orbit the Sunday. This is not coincidence, but a consequence of how the solar system formed from a rotating cloud of gas and dust that flattened as it spun. Objects that don't orbit in the ecliptic plane are usually comets from the Oort cloud or asteroids that have been perturbed by planetary encounters. The ecliptic also represents the apparent path of the Sun across Earth's sky over the year, which is why it's named after eclipses. Lunar and solar eclipses can only occur when the Moon crosses the ecliptic plane. This shared orbital plane links the planets together, evidence of their common origin in a disk of protoplanetary material 4.5 billion years ago. Jupiter's Great Red Spot is shrinking. Historical observations show it was much larger in the past. In the late 1800s, the spot was large enough to fit 3 Earths across. Now it's roughly 1 Earth across. The storm has been observed continuously since the 1600s, making it at least 300 years old, though it might be much older. Scientists don't fully understand why it's shrinking. Changes in Jupiter's internal heat flow or alterations in atmospheric circulation patterns might be affecting the storm. Smaller storms interacting with the Great Red Spot might be siphoning away its energy. Despite shrinking, the Great Red Spot remains the largest storm in the solar system. with wind speeds reaching 270 miles per hour at its edge. It's possible the Great Red Spot might disappear within the next few decades, or could stabilize and persist. Jupiter continues to surprise us with its dynamic, changing atmosphere. Saturn's moon Titan is the only place besides Earth where liquid has been found on the surface. But unlike Earth's water oceans, Titan's lakes and seas contain liquid methane and ethane. Titan's thick nitrogen atmosphere, combined with its cold temperatures, creates a methane cycle remarkably similar to Earth's water cycle. Methane evaporates from lakes, rises to form clouds, and falls as rain. Over time, this rain has carved channels and formed lakes. The largest lake, Kraken Mare, is larger than the Caspian Sea. Scientists have found evidence for changing seasons on Titan, with clouds and rainfall moving between the northern and southern hemispheres as Saturn's seasons progress. One Titan year, equivalent to one Saturn orbit around the Sun, lasts about 30 Earth years. So seasons on Titan are very long. Standing on Titan's surface under an orange hazy sky, you might watch methane rain fall onto methane seas, a landscape alien yet strangely familiar. Earth's water probably came from several sources. Some water was incorporated into the rocks and minerals that formed Earth. As the planet heated, this water was released through volcanic activity. Some water came from comets and asteroids that impacted Earth after it formed. Recent studies of water chemistry suggest asteroids, particularly those from the outer asteroid belt, might have delivered more water than comets. The ratio of hydrogen isotopes in Earth's water more closely matches certain asteroids than most comets. This means the water in Earth's oceans, the water in your body, may have traveled from the outer solar system, carried by asteroids over billions of years. Each drop of water on Earth is ancient, cycled through clouds and rivers and living things countless times. The water you drink today might once have fallen as rain in dinosaur times or been part of an asteroid drifting between Jupiter and Mars. Mercury's surface is covered in cliffs called scarps that stretch for hundreds of miles. These scarps formed as Mercury cooled and contracted. The entire planet shrank by about 4 miles in radius. As the interior cooled and solidified, the crust was forced to buckle, creating these cliffs. Some scarps are up to 2 miles high. Scientists discovered that this contraction happened more recently than expected. Some craters are cut by scarps, meaning the scarps formed after the craters. This suggests Mercury's interior remained warm longer than models predicted. Even small worlds can harbor surprises. Mercury, the smallest planet, closest to the Sun, baked and frozen in turn, still has stories to tell about the solar system's history. Its wrinkled surface records the slow cooling of a small rocky world. Venus has more volcanoes than any other planet. Over 1,600 major volcanoes or volcanic features have been identified, and there are likely many more small ones. These volcanoes are scattered across the surface, along with vast volcanic plains where lava once flowed. Whether any of these volcanoes are currently active is uncertain. Some recent observations have detected changes in sulfur dioxide levels in Venus's atmosphere, which could indicate ongoing volcanic activity. But confirming this is difficult. Venus's thick clouds hide the surface from direct observation. We can only see through the clouds using radar. The Soviet Venera landers that reached the surface sent back images showing flat rocks that looked like volcanic basalt. Venus's geology appears to be dominated by volcanism, perhaps because the thick crust and hot interior create conditions where volcanic activity is common. The planet may periodically resurface itself through massive volcanic episodes. Mars's 2 small moons, Phobos and Deimos, might not be captured asteroids after all. Recent studies suggest they could have formed from debris blasted into orbit by a massive impact on Mars, similar to how Earth's moon formed. The shape and composition of Phobos and Deimos resemble asteroids, but their orbits are unusual for captured objects. They orbit in almost perfectly circular paths aligned with Mars's equator, which would be unlikely if they were captured. Computer simulations show that a large impact on Mars could have created a disk of debris that formed into several moons. Over time, all but Phobos and Deimos fell back to Mars or were ejected. This theory is still debated, but it highlights how even well-studied objects can surprise us. The origin of moons, even small ones, connects to the violent history of planetary formation. Saturn's rings are made of countless pieces of ice and rock, but the rings are not solid structures. Each particle orbits Saturn independently, following its own path determined by Saturn's gravity. The rings are held in place by a balance between gravity pulling particles inward and the particles' orbital motion carrying them outward. Gaps in the rings occur where Moon's gravity clears out material. The Cassini division, a large gap between the A and B rings, is caused by gravitational resonances with Saturn's moon, Mimas. Particles in the Cassini division orbit Saturn exactly twice for every one orbit Mimas makes. This resonance allows Mimas's gravity to gradually pull particles out of that region. Similar resonances with other moons create other gaps. The rings are dynamic, constantly evolving as particles collide, stick together, and break apart. What we see today is a snapshot of a structure that's slowly changing. Pluto has 5 known moons. The largest, Charon, is about half Pluto's size. The other 4, Styx, Nix, Kerberos, and Hydra, are much smaller, ranging from about 6 to 30 miles across. These small moons have highly reflective surfaces and irregular shapes. They all orbit in the same plane as Charon and are tidally locked to the Pluto-Charon binary system, though not to Pluto or Charon individually. Scientists think the entire Pluto system formed from debris left over when 2 Kuiper belt objects collided. Pluto and Charon formed from the largest pieces, while the smaller moons formed from other debris. The New Horizons mission provided our first close-up views of these moons in 2015, revealing them to be icy, cratered worlds. Finding 5 moons around such a distant dwarf planet was unexpected and shows that even the outer solar system holds complexity and surprises. The Sun contains 99.86% of the solar system's total mass. All the planets, moons, asteroids, comets, and dust combined make up only about 0.14%. Jupiter alone accounts for most of that 0.14%. If you gathered all the material in the solar system, except the Sun, Jupiter would still be by far the largest object, containing more than twice the mass of all the other planets combined. This enormous mass disparity shows how star formation works. When the solar system formed from a collapsing cloud of gas and dust, most of the material fell into the center, forming the Sunday. Only a small fraction remained in the disk surrounding the young Sun, and from that disk, the planets formed. We live in a system dominated by our star, minor worlds orbiting a massive central body that provides light, heat, and gravity. Neptune's moon Triton has a tenuous atmosphere, mostly nitrogen, with small amounts of methane. Surface pressure is extremely low, about 70,000 times less than Earth's. Despite this thin atmosphere, Triton has active nitrogen geysers that erupt through the surface ice. These geysers reach altitudes of 5 miles, where they're caught by winds and form long dark streaks across the ice. The geysers are thought to be driven by solar heating. Even though Triton is so far from the Sun, the surface ice is transparent enough that sunlight penetrates several feet down. This creates a solid-state greenhouse effect. The warmed subsurface nitrogen vaporizes, pressure builds beneath the ice, and eventually it bursts through in a geyser. Triton's surface shows relatively few impact craters, suggesting the surface is young, perhaps only a few 100 million years old. This activity on such a distant, cold moon continues to puzzle scientists. The asteroid belt contains millions of objects, but if you added all their mass together, it would be less than 4% of the moon's mass. The belt is not densely packed, Space probes have flown through the asteroid belt many times without any danger of collision. The asteroids are spread across an enormous volume of space. Most are very small, just a few feet across, though a few, like Ceres and Vesta, are hundreds of miles in diameter. The asteroid belt exists where it does because Jupiter's gravity prevented a planet from forming there. Jupiter's gravitational influence stirred up the orbits of objects in that region, causing them to collide at high speeds. These collisions tended to break objects apart rather than allowing them to grow larger. The asteroid belt is a graveyard of planetary formation, a region where a planet never managed to assemble. Uranus has 13 known rings, though they're much fainter and narrower than Saturn's. The rings were discovered in 1977 when astronomers watched Uranus pass in front of a star. The star's light blinked off and on several times before and after Uranus blocked it, revealing the rings. The rings are dark, reflecting only a few % of the light that hits them, possibly because they're made of dark, organic material rather than bright ice. The rings are extremely narrow, some only a few miles wide. Shepherd moons orbit near some rings, their gravity helping to keep ring particles confined in narrow bands. The rings might be relatively young, perhaps formed when a small moon was shattered by an impact. As ring particles collide, they gradually darken and eventually fall onto Uranus. Uranus's rings might disappear entirely over millions of years. Io's surface is constantly being renewed by volcanic eruptions, which means there are no impact craters visible on its surface. Anywhere a crater forms is quickly buried by fresh lava or coated with sulfur compounds from volcanic plumes. This makes Io's surface the youngest in the solar system. Estimates suggest the entire surface is replaced every million years or so, incredibly fast in geological terms. By studying Io, scientists can observe volcanism in action on a scale that doesn't happen on Earth. Io's volcanoes provide a laboratory for understanding volcanism throughout the solar system. Similar processes might occur on exoplanets orbiting close to their stars, where tidal forces could drive intense volcanic activity. Io is a window into planetary processes that shape worlds throughout the galaxy. It's a tortured moon, squeezed relentlessly by Jupiter's gravity, erupting constantly, never resting. The Sun's corona, its outer atmosphere, is much hotter than its visible surface. The surface temperature is about 10,000 degrees Fahrenheit, while the corona reaches temperatures exceeding 1 million degrees. This seems to violate basic physics. How can the atmosphere be hotter than the surface below? Scientists have debated this coronal heating problem for decades. The answer likely involves magnetic fields. The Sun's magnetic field lines extend through the corona, storing energy. When these field lines reconnect or snap, they release energy that heats the corona. Small-scale magnetic reconnection events might constantly heat the corona to such high temperatures. The Parker Solar Probe mission is helping to solve this mystery by flying through the corona and making direct measurements. Understanding coronal heating helps us predict space weather events that can affect Earth. The corona teaches us that proximity to a heat source doesn't always determine temperature when magnetic forces are at play. Close your eyes and let each breath guide you. Time is yours, a separate stream that only you are living. While the vast universe continues to spin, expand, change, this second you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe. Even when everything seems empty, space is always full of waves, vibrations, invisible energy. The space inside and around you is never truly empty. Imagine you're floating on a calm lake, but beneath the surface, there's always gentle current. Now we continue the journey. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spacecraft orbit Earth. Earth orbits the Sunday. The Sun orbits the center of the Milky Way. All are circles, cycles, endless orbits. Like your breath, Inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. Every sunrise and sunset you watch, the light has traveled 8 minutes from the Sunday. Each photon of light, generated deep in the sun's core, works its way outward over thousands of years before finally escaping into space. Then it speeds toward Earth at 186,000 miles per second, arriving 8 minutes later. When you feel warmth on your skin, you're feeling light that began its journey in a fusion reaction deep within the Sunday. That ancient light, carrying energy across space, connects you to the star at the center of our system. It's sunlight that powers photosynthesis, creating food. It's sunlight that drives weather. Every living thing on Earth depends on light from a star 93 million miles away. The moon shows phases because of its position relative to Earth and the Sunday. When the moon is between Earth and the sun, we see the side in darkness, a new moon. When Earth is between the moon and the sun, we see the fully lit side, a full moon. The cycle from new moon to full moon and back takes about 29.5 days. Ancient calendars based themselves on these lunar cycles. We still organize months roughly around the moon's phases. The word month comes from moon. For thousands of years, humans watched the moon wax and wane, using its predictable cycle to mark time. Even now, when we have atomic clocks, the moon still measures time in its ancient rhythm. Jupiter protects Earth from some asteroids. Its powerful gravity deflects or captures objects that might otherwise fall toward the inner solar system. Some comets that approach Jupiter are pulled in and destroyed. The Shoemaker-Levy 9 comet broke apart and crashed into Jupiter in 1994, creating impact scars larger than Earth. We watched those impacts in real time, a reminder of how violent collisions can be. Jupiter also sends objects inward sometimes, so it's not a perfect shield, but its presence alters the distribution of objects in the solar system. We might owe our existence partly to Jupiter. Without it, Earth might have experienced many more impacts, possibly preventing complex life from evolving. Jupiter is our neighbor, and, in a way, our protector. Neptune glows blue, not just from methane, but from an unknown component in its atmosphere. Uranus has similar amounts of methane, but appears more cyan. Scientists think there's an additional layer or molecule in Neptune's atmosphere that absorbs red light more strongly, making Neptune appear a deeper blue. This mystery molecule has not yet been identified. Neptune's beautiful color reminds us that even familiar worlds hold unknowns. The atmosphere flows and swirls in patterns we're only beginning to understand. Neptune, far from the sun, cold and distant, glows like a sapphire in the darkness. Its color is a puzzle waiting to be solved. Saturn's moon, Enceladus, might have the right conditions for life. Its subsurface ocean contains water, organic molecules, and chemical energy from reactions between water and rock. These are the basic requirements life needs. Whether life actually exists there, we don't know. But Enceladus teaches us that life's ingredients can exist in unexpected places. An ocean beneath the ice of a small moon, orbiting a distant planet, warmed by tidal forces, might harbor microbes. If we find life there, it would tell us life is common in the universe. If we don't, it would tell us life is precious and rare. Either answer would be profound. Enceladus waits, ice and water and mystery. Earth's atmosphere protects us from meteoroids. Most objects smaller than a car burn up completely due to friction with air molecules before reaching the ground. We see these as meteors or shooting stars. About 100 tons of space dust and tiny meteoroids enter Earth's atmosphere every day, most of it burning up harmlessly. Occasionally, larger objects survive and become meteorites. These meteorites contain material from the early solar system. Scientists study them to learn about how planets formed. The atmosphere shields us invisibly, a blanket of air protecting the surface. We rarely think about how much debris falls toward Earth from space. The atmosphere quietly defends us every day. Mars has polar ice caps made of frozen water and frozen carbon dioxide. In winter, carbon dioxide freezes out of the atmosphere and adds to the polar caps. In summer, it sublimes back into gas. The water ice beneath remains frozen year-round. These seasonal changes cause Mars's atmospheric pressure to vary by about 25% over a Martian year. The polar caps advance and retreat with the seasons, changing the landscape. From orbit, spacecraft watch these cycles, measuring how much ice accumulates and disappears. Mars breathes with its seasons, freezing and thawing, a rhythm billions of years old. Beneath the ice, layers record climate history, each layer representing a different era. The Great Red Spot on Jupiter is shrinking, but it remains larger than Earth. The storm's winds rotate counterclockwise, and wind speeds reach hundreds of miles per hour at the edges. Inside, conditions are more complex. The spot is essentially a high-pressure system, with gas rising in the center and sinking at the edges. The storm's color may come from chemicals brought up from deeper in Jupiter's atmosphere, possibly containing sulfur or phosphorus compounds that change color when exposed to sunlight. The Great Red Spot has fascinated observers for centuries. It may someday disappear, but for now, it endures. A storm so large and long-lived, it defies comparison to anything on Earth. Titan's atmosphere is thicker than Earth's. If you stood on Titan, you'd feel pressure about 1.5 times greater than at sea level on Earth. Not crushing, but noticeably heavier, like standing a few feet underwater. The atmosphere is mostly nitrogen, just like Earth's, but Titan is far too cold for liquid water. Instead, methane plays water's role. Methane evaporates, forms clouds, and falls as rain. Rivers of methane carve valleys. Lakes of methane fill crater basins. Titan is a world where familiar processes happen with unfamiliar materials. Organic molecules form in the atmosphere and drift down as haze. The surface is coated with organic material, rich in carbon chemistry. Titan is perhaps the most Earth-like body in the solar system, yet profoundly alien. Mercury orbits the Sun faster than any other planet. It completes one orbit in just 88 Earth days. It moves at an average speed of 29 miles per second. This is partly because it's close to the Sun, where orbital speeds are higher. Mercury races around the Sun, baked by intense sunlight, its surface alternately roasting and freezing. Its rapid orbit has been known since ancient times. To ancient astronomers, Mercury appeared to move quickly across the sky. They named it after the swift messenger god. Mercury lives up to its name, speeding through space, the fastest planet, closest to the light. Venus's atmosphere rotates faster than the planet itself. The clouds circle Venus in about 4 days, while the planet takes 243 days to rotate once. This is called superrotation, and it's not fully understood. Somehow, the atmosphere has decoupled from the surface and spins much faster. Winds in the upper atmosphere reach speeds of 224 miles per hour. These winds carry heat from the day side to the night side, keeping temperatures fairly uniform across the planet despite the slow rotation. Venus is full of puzzles. Its atmosphere moves independently, governed by laws we're still trying to understand. Sunlight pushes on objects. Light has momentum, and when photons hit something, they transfer that momentum. This force is incredibly weak, but in space, where there's no air resistance, it adds up over time. Solar sails use this principle. A large, reflective sail can be pushed by sunlight, slowly accelerating a spacecraft without needing fuel. This is how light can push comet dust into tails, how tiny particles in the solar system are gradually pushed outward by the sun's light. Sunlight is not just light and warmth. It's a gentle but persistent force, shaping the solar system in subtle ways. Even light exerts pressure, a reminder that everything is connected through physics. Mars's largest volcano, Olympus Mons, rises so high that its summit extends above much of Mars's thin atmosphere. At the top, atmospheric pressure is extremely low. If you stood there, you'd see the sky fade to black, a view closer to space than to the surface. The volcano's gentle slopes mean you could drive to the summit. It would be a long drive, but there are no cliffs or steep sections. Olympus Mons formed over billions of years through countless eruptions. Each lava flow added a thin layer. Over time, these layers built up into the largest volcano in the solar system. It's probably no longer active, a relic of Mars's volcanic past, silent and towering. Earth's moon has no atmosphere to speak of. The surface is exposed directly to space. Sunlight heats the surface to 250 degrees Fahrenheit. In shadow, temperatures plunge to -280 degrees. There's no air to distribute heat or soften these extremes. Footprints left by Apollo astronauts will last for millions of years because there's no wind or weather to erode them. The sky is always black, stars visible even in full daylight. The moon is a silent world, airless and still, an ancient companion to Earth, shining in the night. Jupiter's intense radiation belts would be dangerous for humans. Any spacecraft passing through must be heavily shielded. The Europa Clipper mission is designed to withstand this radiation for years while orbiting Jupiter. Io orbits within the most intense radiation zone. Any organism on Io's surface would be sterilized by radiation. Even electronic equipment must be specially hardened. Jupiter's magnetosphere accelerates particles to extremely high energies. These particles spiral along magnetic field lines, creating auroral emissions and powerful radio bursts. Jupiter generates its own radiation environment, hostile and energetic. It's a reminder that not all space is empty and gentle. Some regions are violent, filled with invisible but dangerous forces. Saturn's rings may be younger than the dinosaurs. Some scientists estimate the rings could be only a few 100 million years old, formed when a comet or moon broke apart. If true, the rings are a temporary feature. In another 100 million years, they might fade away as material falls into Saturn or is ejected. We're fortunate to see them now. Ancient peoples who looked up never saw Saturn's rings because humans didn't have telescopes. When Galileo first observed Saturn in 1610, his telescope was barely strong enough to show the rings. He thought Saturn had 2 large moons on either side. Later, better telescopes revealed the truth. Saturn's rings are beautiful and fragile, a cosmic ornament that won't last forever. Neptune has completed only about 1.5 orbits since it was discovered in 1846. It takes 165 Earth years to orbit the Sun once. In July 2011, Neptune completed its first full orbit since discovery. Humans have not yet watched Neptune complete 2 full journeys around the Sunday. This is a reminder of how slowly outer planets move. From our perspective, they drift slowly across the sky against the background stars. Ancient astronomers knew Mercury, Venus, Mars, Jupiter, and Saturn because they could see them and track their motion over years. Neptune and Uranus remained hidden until telescopes revealed them. Neptune is so distant and slow that its orbit becomes a measure of human time. It hasn't yet completed 2 passages around the Sun during human recorded history. Pluto's surface shows different regions with different colors and compositions. The heart-shaped region called Tombaugh Regio is brighter because it's covered in nitrogen ice. Dark regions may be areas where methane has been converted into darker organic compounds by radiation. Pluto's surface is young in places, suggesting geological activity. How a world so small and so cold remains active is still debated. Perhaps radioactive decay in the core provides some heat. Perhaps gravitational interactions with Charon generate tidal heating. Pluto defied expectations. It's not a dead ice ball but a complex, evolving world. Even in the outer reaches of the solar system, change happens. Surfaces renew, mountains rise, ice flows. Nothing in the solar system is truly static. Comets that pass close to the Sun can develop tails millions of miles long. The Great Comet of 1844 had a tail visible even in daylight, stretching across half the sky. Yet the nucleus, the actual solid body of the comet, might have been only a few miles across. Most of a comet's volume is empty space. The tail is incredibly diffuse, with fewer particles per cubic yard than what we call a vacuum on Earth. If you flew through a comet's tail, you might not even notice. Yet from a distance, the tail shines brilliantly, reflecting sunlight. Comets are ghosts, mostly emptiness, yet they blaze across the sky, visible for weeks or months before fading back into the darkness beyond. The asteroid belt separates the inner rocky planets from the outer gas giants. This division isn't arbitrary. It marks a boundary in the solar system where temperatures and conditions changed during formation. Inside this line, temperatures were high enough that water remained as vapor, so rocky planets formed. Beyond this line, water could condense as ice, allowing larger objects to form by accumulating not just rock, but also ice. This is why the outer planets grew so large. They captured not just rock, but also vast amounts of water, ammonia, and methane. Jupiter and Saturn captured even more, pulling in hydrogen and helium, becoming gas giants. The asteroid belt is a border region, a dividing line between two different kinds of worlds. The Moon's influence on Earth goes beyond tides. The Moon stabilizes Earth's axial tilt, preventing it from wobbling wildly. Without the Moon, Earth's tilt could vary chaotically over millions of years, causing drastic climate swings. Some scientists think this stability was important for life's evolution. Stable climates allowed life to adapt gradually, rather than facing constant, extreme changes. Mars, with no large moon, has experienced dramatic shifts in axial tilt, perhaps contributing to its loss of atmosphere and surface water. The Moon has been Earth's steady companion, quietly keeping our planet stable, allowing life to flourish. We orbit together, Earth and Moon, locked in a dance that has lasted billions of years. Io's volcanoes don't erupt lava the way Earth's do. The lava is hotter, reaching temperatures up to 3,000 degrees Fahrenheit. This extreme heat makes Io's lava very fluid, flowing rapidly across the surface. Some eruptions create massive lava fountains. Others produce long flows that spread across the Moon's surface. Sulfur compounds ejected by the volcanoes give Io its yellow and orange colors. The landscape is constantly changing, resurfaced by eruptions. Standing on Io would be like standing in hell. The ground would shake, lava would erupt around you. The sky would be filled with volcanic plumes. Yet from orbit, Io looks almost beautiful. A colorful, dynamic world, unlike any other. Saturn's moon Mimas is sometimes called the Death Star moon because of its huge crater. The impact that created Herschel crater nearly destroyed Mimas. Fractures on the opposite side of the moon show where shock waves traveled through Mimas and fractured the ice. If the impactor had been slightly larger or slightly faster, Mimas would have shattered into fragments. Instead, it survived, barely. The crater is a reminder of how violent the solar system can be. Impacts of this scale are rare now, but early in the solar system's history, they were common. Many worlds show scars from ancient collisions. Mimas's crater is just one of countless impacts that shaped the solar system we see today. Neptune's winds are the fastest, but Uranus has the calmest atmosphere of any giant planet. When Voyager 2 flew past Uranus in 1986, it saw hardly any clouds or storms. The atmosphere appeared almost featureless. Scientists wondered if they had arrived during an unusually calm period. Later observations with Hubble and ground-based telescopes revealed that Uranus does have storms, but they're rare and appear mostly during its long seasons when one pole points toward the Sunday. Uranus's extreme axial tilt affects its weather. The pole facing the Sun heats up over decades, gradually driving atmospheric circulation. Uranus is slow to respond, quiet most of the time, occasionally stirring into activity. It's a gentle giant, tilted on its side, slowly turning in the distant darkness. Every object in the solar system, from the Sun to the smallest asteroid, is moving through space together. We orbit the center of the Milky Way galaxy at about 137 miles per second. Our entire solar system, all the planets and moons, comets and dust, all of it is traveling together through the galaxy. We're part of something much larger, a galaxy containing hundreds of billions of stars, each perhaps with its own worlds. And our galaxy is moving through the universe, pulled by gravity toward other galaxies. We're in motion, always in motion, part of an ancient cosmic dance that began with the Big Bang and continues still. Everything is connected, everything is moving, and we're all traveling together through space and time. And so, our quiet journey through the solar system comes to a gentle close. We've traveled from the glowing surface of the Sun, where Parker Solar Probe flies through million-degree heat, to Neptune, where diamonds rain through hydrogen atmospheres, discovering along the way that our cosmic neighborhood is filled with both familiar patterns and profound mysteries. From Europa's hidden ocean to Io's volcanic rage, from Mars's ancient river valleys to Titan's methane lakes, we've glimpsed how each world is both unique and part of the same ancient story. The solar system reminds us that we're part of something larger than ourselves. Much of the most fascinating activity happens in silence, beneath ice shells, in distant orbits, in the darkness, far from the Sunday. These worlds teach us patience and wonder. Without curiosity about what lies beyond our sky, we would never have discovered these distant places. By pausing to notice, we glimpse the extraordinary in the ordinary. We are, after all, made of stardust, orbiting a common star, sharing this small corner of the galaxy. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity, of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about the unity of every atom in space, where all boundaries dissolve. Light, matter, time, all becoming one. You too can dissolve into sleep like that, no boundaries left between you and rest. Let your entire being dissolve into the gentle darkness, into the soft gravity pulling you into sleep. Prepare for deep sleep, no boundaries left, only peace. If this gentle journey through the cosmos brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of planets and moons to fade now, like stars fading into dawn light, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Jupiter's gentle gravity is pulling you down into comfort. If sleep comes, let it carry you like a spacecraft, coasting through silent space, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the sun will still shine. The planets will still orbit. The moons will still circle their worlds. But tonight belongs to stillness. Rest well, space traveler. And remember, we are all made of stars, drifting through the universe together. Fall asleep to gentle facts. Dream deeper with bedtime science. Good night.